You know, there's something deeply unsettling about the fact that we've been using quantum mechanics for almost a century now, and yet we still can't agree on what actually happens when we make a measurement. We can build quantum computers, we can teleport quantum states across laboratories, we can do all these incredible things. But ask a room full of physicists what really happens when an electron's position gets measured, and you'll start an argument that could last until morning. This isn't just some philosophical nitpicking either. The measurement problem sits at the absolute core of quantum mechanics, and the fact that it remains unsolved tells us something profound. We might be missing something fundamental about the nature of reality itself. Let me start with a simple question that will guide us through this entire exploration. When you're not looking at an electron, where is it? Your intuition probably says it's somewhere specific. We just don't know where. But quantum mechanics says something far stranger. It's not really anywhere until you look. And that's where all our troubles begin. Part 1. Setting up the mystery. What we mean by measurement. Before we dive into why measurement is problematic, we need to understand what physicists actually mean by this word. In quantum mechanics, a measurement isn't just passively observing something like watching a bird through binoculars. It's an interaction between a quantum system and a measuring device that produces a definite classical result. Think about measuring the position of an electron. Before the measurement, quantum mechanics describes that electron with something called a wave function, usually written as the Greek letter psi. This wave function spreads out through space, and here's the crucial part. It represents the electron existing in a superposition of many different positions simultaneously. Now, the wave function itself doesn't directly tell you where the electron is. Instead, the square of its amplitude at any point tells you the probability of finding the electron there if you measure it. This is the Born rule, named after physicist Max Born, and it's been verified experimentally countless times with extraordinary precision. But here's where things get weird. When you actually do measure the electron's position, you don't get a probability. You get a specific location. The electron appears here, not there. The measurement yields a definite outcome, even though the wave function said the electron was somehow in many places at once. The two types of evolution. This brings us to what physicist John Bell called the shifty split in quantum mechanics. The theory describes two completely different types of evolution, and nobody can quite explain why both exist or where the boundary between them lies. The first type is Schrödinger evolution, named after Erwin Schrödinger and his famous equation. This evolution is smooth, continuous, deterministic, and reversible. When a quantum system isn't being measured, its wave function evolves according to the Schrödinger equation in a perfectly predictable way. If you know the wave function now, and you know the system's Hamiltonian, which represents its energy, you can calculate exactly what the wave function will be at any future time. You can even run the calculation backward and figure out what it was in the past. The second type happens during measurement. It's called wave function collapse. and it's the complete opposite of Schrödinger evolution. It's sudden, discontinuous, irreversible, and fundamentally random. The spread-out wave function instantaneously collapses to a single outcome, picked randomly from the range of possibilities with probabilities given by the Born rule. These two processes couldn't be more different. It's like the universe follows one set of rules most of the time, then suddenly switches to a completely different set of rules whenever a measurement happens. But quantum mechanics never actually tells us what counts as a measurement or why measurements should be special. Part 2. Why this is actually a problem. The Heisenberg cut. Werner Heisenberg tried to address this schizophrenic behavior by proposing something called the Heisenberg cut. He suggested we should divide the world into two realms, the quantum system being observed and the classical measuring apparatus doing the observing. The quantum system evolves according to the Schrödinger equation until it interacts with the classical apparatus, at which point collapse happens. But this just pushes the problem back a step. Where exactly do you draw this line? Is it at the detector? At the readout device? At the experimentalist's eye? At their brain? And more fundamentally, if everything in the universe is ultimately made of quantum particles, how can there be a truly classical realm that's exempt from quantum rules? Think about it this way. Your measuring device is made of atoms. Those atoms are quantum mechanical objects. So when the quantum system interacts with your measuring device, why doesn't the combined system of particle plus apparatus just evolve according to the Schrödinger equation? Why does collapse happen instead? If you try to apply the Schrödinger equation to the combined system, you get something deeply strange. The electron's superposition of positions becomes entangled with the measuring device's pointer, creating a superposition where the device simultaneously shows multiple different readings. But we never see this. We always see one definite pointer position. Von Neumann's infinite regress. Mathematician John von Neumann explored this problem in rigorous detail in his 1932 book, Mathematical Foundations of Quantum Mechanics. He showed that you can keep pushing the Heisenberg cut further and further out. You can include the measuring device in your quantum description, but then you need another device to measure that one. You can include the second device, but then you need a third. You can include the experimenter's eyes, their brain, even their consciousness. Von Neumann actually proved mathematically that it doesn't matter where you put the cut, at least not for predicting experimental outcomes. You always get the same probabilities for measurement results. But while this is convenient for making predictions, it doesn't solve the conceptual problem. It just shows that the problem can be postponed, not eliminated. This is what philosophers call the problem of infinite regress. To explain measurements, you need something outside the quantum system to collapse it. But that something is itself made of quantum particles, so it needs something else to collapse IT, and so on forever. You never find a stopping point where collapse actually happens. Schrödinger's cat. Problem made. Vivid. Erwin Schrödinger invented his famous cat thought experiment in 1935, specifically to show how absurd this situation becomes if you take quantum mechanics seriously. The setup is probably familiar, but let me walk through it because the details matter. You put a cat in a sealed box with a vial of poison, a radioactive atom, and a detection device. The atom has a 50% chance of decaying within 1 hour. If it decays, the detector triggers a mechanism that breaks the vial and kills the cat. If it doesn't decay, the cat lives. Now, quantum mechanics says that after 1 hour before you open the box, the radioactive atom exists in a superposition of decayed and not decayed. That's uncontroversial. But if the atom is in superposition and the detector is entangled with the atom, then the detector is in a superposition of triggered and not triggered. And if the detector is in superposition, the vial is in a superposition of broken and intact. And therefore the cat is in a superposition of dead and alive. Schrödinger found this ridiculous. He wrote, "One can even set up quite ridiculous cases. A cat is penned up in a steel chamber along with the following device. It is typical of these cases that an indeterminacy originally restricted to the atomic domain becomes transformed into macroscopic indeterminacy, which can then be resolved by direct observation." The point wasn't that Schrödinger actually believed in half-dead cats. He was showing that something goes wrong when you try to apply quantum mechanics to macroscopic objects. The theory seems to work perfectly for electrons and atoms, but it generates nonsense when you scale it up. This suggests that either the theory is incomplete or our interpretation of it is deeply flawed. Part 3. What collapse would actually require the mathematical structure of collapse? Let's get more precise about what wave function collapse would actually mean mathematically, because this will help us understand why it's so problematic. In quantum mechanics, the state of a system is represented by a vector in something called Hilbert space. This is an abstract mathematical space that can have infinitely many dimensions. A superposition is just a sum of different vectors in this space. For example, an electron in a superposition of being at position A and position B is represented by a vector that's a sum of the vector for electron at A and the vector for electron at B. When collapse happens, this vector somehow changes into just one of the components of that sum. The superposition vector transforms into either electron at A or electron at B, with probabilities determined by the Born rule. But here's the thing, this transformation isn't described by the Schrödinger equation. It's not described by any equation in the theory. It's just stated as a separate postulate. This is extraordinarily unusual for a physics theory. Imagine if Newton's laws of motion said, objects follow F equals ma, except when they don't, and we won't tell you when those exceptions occur. That would be unacceptable. But quantum mechanics essentially does exactly this. Moreover, collapse has to be non-local if it's real. Suppose you have two entangled particles separated by a large distance. The wave function describes them as a single, non-separable entity. If you measure one particle and collapse happens, the wave function for the other particle far away must also instantaneously change. Einstein called this spooky action at a distance. and he found it deeply troubling. Information and irreversibility. There's another profound issue with collapse. It destroys information. Remember, Schrödinger evolution is reversible. If you know the wave function at time B, you can calculate what it was at time A. The information is preserved, but collapse is irreversible. Once the superposition collapses to one outcome, you can't recover what the full superposition was. The information about the other possible outcomes is simply gone. This seems to violate a deep principle in physics. In classical mechanics, in special relativity, in general relativity, even in quantum field theory, when you're not talking about measurement, the fundamental laws are all time reversible. They work the same whether time runs forward or backward. Information is conserved. But measurement, if collapse is real, introduces a fundamental arrow of time and destroys information. This bothered many physicists, particularly John Wheeler, who spent much of his later career arguing that information must be fundamental to physics. How can a complete physical theory have a process that simply erases information? Where does it go? The preferred basis problem. Here's yet another subtle but crucial issue. When collapse happens, the wave function collapses into states from a particular basis. But what determines that basis? Let me explain what I mean. In quantum mechanics, you can describe a system using different sets of basis states, and they're all equally valid mathematically. For example, an electron's spin can be described using the up-down basis or the left-right basis or any rotated basis you choose. These are all just different ways of representing the same physical reality. But when measurement happens, collapse picks out a specific basis, the eigenbasis of whatever observable you're measuring. If you measure spin in the up-down direction, the wave function collapses into either spin-up or spin-down in that direction. If you measure spin in the left-right direction, it collapses into either spin-left or spin-right. This means the collapse postulate requires specifying not just that collapse happens, but also what it collapses into. And that depends on the measurement being performed. But if the measuring device is itself a quantum system, why should its particular physical properties determine a special basis for collapse? Why don't other bases work just as well? This is called the preferred basis problem, and it shows that collapse seems to require something external to quantum mechanics to specify which basis is special. Part 4. The major interpretations and their strategies. Strategy 1. Copenhagen and its variants, accepting the split. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, doesn't really solve the measurement problem so much as it declares it unsolvable, or perhaps meaningless. The core idea is that quantum mechanics only describes what we can know about systems through measurements, not what systems are actually like independently of measurement. The wave function isn't a real physical thing. It's just a tool for calculating probabilities of measurement outcomes. Asking what happens between measurements is like asking what happens between acts of a play when the curtain is down. It's not part of the story. Bohr introduced the concept of complementarity to handle this. He argued that quantum systems have complementary properties like position and momentum that cannot be measured simultaneously with perfect precision. This isn't just practical limitation, it's a fundamental feature of reality. The properties only exist in the context of specific experimental arrangements. An electron doesn't have a definite position when you're measuring its momentum. Position only becomes real when you set up a position measurement. This interpretation has the advantage of being practical and avoiding metaphysical speculation. It focuses on what we can actually observe and measure, which is exactly what physicists need to do their work. That's why it dominated for decades and is still the default view in many physics textbooks. But critics point out that Copenhagen doesn't really explain anything. It just forbids certain questions. It treats measurement as primitive and classical reality as fundamental, without explaining why measurement should be special or how classical reality emerges from quantum mechanics. When pressed on where exactly the wave function collapses, Copenhagen advocates often give vague answers about the importance of irreversible amplification or the creation of permanent records, but they don't make these notions mathematically precise. The physicist N. David Mermin once summarized Copenhagen's attitude with the phrase, "shut up and calculate." The interpretation tells you how to use quantum mechanics to make predictions, but it doesn't tell you what's really going on. Strategy 2. Many worlds, keeping everything quantum. Hugh Everett proposed something radically different in his 1957 doctoral thesis. What if collapse never actually happens? What if the Schrödinger equation always applies, even during measurements, and the appearance of collapse is just an illusion? Here's how it works. When you measure an electron's position, the combined system of electron plus apparatus plus you goes into a superposition where each possible outcome actually occurs, but in a different branch of reality. The universe splits into multiple parallel worlds, and in each world, one specific outcome happened. From inside any particular branch, it looks like collapse occurred and you got one random outcome. But from a God's eye view, all outcomes happened. This interpretation has a beautiful simplicity to it. There's only one law of evolution, the Schrödinger equation, which always applies without exception. There's no measurement problem because there's no collapse. Every possible outcome of every quantum measurement actually happens in some branch of the universal wave function. Many worlds also handles the non-locality issue differently than Copenhagen. When you measure one member of an entangled pair, the universe branches, but there's no instantaneous action at a distance within any particular branch. The correlations between distant measurements are explained by the branching structure, not by faster-than-light influences. But many worlds faces its own serious problems. The most obvious is that it seems wildly extravagant ontologically. Every quantum measurement spawns countless new branches of reality, most of which we never experience. Schrödinger's cat isn't half dead. Instead, there are two fully real universes, one with a dead cat and one with a living cat. The number of branches grows exponentially with every quantum interaction, and there are quantum interactions happening everywhere all the time. Then there's the problem of probability. If all outcomes actually happen, why do we experience them with the frequencies given by the Born rule? In a universe where you split into one copy that sees heads and one copy that sees tails, why should you expect to see heads 2/3 of the time if the quantum amplitude favors heads? Both outcomes happen with certainty. Many world's advocates have proposed various solutions to this probability problem, but none are universally accepted. There's also the preferred basis problem again. The universal wave function is just a mathematical object. It doesn't come pre-divided into branches. The division into branches requires choosing a preferred basis, but Everett's theory doesn't specify which basis to use. You need something extra, beyond the Schrödinger equation itself, to explain why we see definite measurement outcomes rather than superpositions. Strategy 3. De Broglie-Bohm, adding hidden variables. Louis de Broglie originally proposed this idea in 1927, but it was largely forgotten until David Bohm rediscovered and developed it in 1952. The strategy here is to say that quantum mechanics, as usually presented, is incomplete. There are additional variables that the theory doesn't describe, and these hidden variables determine the actual measurement outcomes. In Bohm's version, particles always have definite positions, even when we're not measuring them. The wave function is also real and exists alongside the particles. The wave function guides the motion of the particles through something called the quantum potential, and the particles in turn don't affect the wave function. When you make a measurement, you're discovering where the particle actually was, not causing collapse. This interpretation is deterministic. If you knew both the wave function and the precise positions of all particles, you could predict with certainty what any measurement would yield. But we can't know the exact initial positions, so in practice the theory makes the same probabilistic predictions as standard quantum mechanics. De Broglie-Bohm has several appealing features. It restores determinism to quantum mechanics. It explains why measurements yield definite outcomes. Particles have definite positions, so of course you get a definite result when you detect one. And it provides a clear ontology, a story about what's actually there in physical reality. But it has costs too. The theory is explicitly non-local. The quantum potential acts instantaneously across space, so measuring one particle immediately affects the motion of distant entangled particles. This doesn't violate relativity's ban on faster-than-light signaling, but it does seem to conflict with the spirit of relativity, which says distant events shouldn't instantaneously influence each other. There's also the problem of generalizing beyond position. Bohm's original theory assigns definite values to particle positions, but not to other properties like spin. Later versions have been developed that treat spin and other observables as Beebles, real properties, but these become increasingly complicated. And there's a philosophical worry. Why should nature be described by these hidden variables that we can never actually measure, not even in principle? The theory is constructed precisely so that the hidden variables can't be detected directly. Some physicists find this unsatisfying. Part 5. Modern Approaches and Developments. Decoherence. The partial solution. In the 1970s and 1980s, physicists started developing the theory of decoherence, and it genuinely represented progress on the measurement problem, even though it doesn't completely solve it. The key insight is that real quantum systems are never truly isolated. They're always interacting with their environment, air molecules bouncing off them, photons scattering from them, thermal vibrations in their supporting structures, and so on. These environmental interactions cause the quantum system to become entangled with its surroundings very rapidly. When a quantum system becomes entangled with a large, complex environment, something remarkable happens. The off-diagonal elements of the density matrix, which represent quantum coherence between different states, get suppressed extremely quickly. This is decoherence. The system effectively behaves classically, even though technically it's still in a quantum superposition with the environment. Let me be more concrete. Consider Schrödinger's cat again. In reality, a superposition of dead cat and alive cat states wouldn't persist for even a fraction of a second. The two states differ in the positions and momenta of trillions upon trillions of molecules. Each of those molecules interacts with photons and air molecules and the walls of the box. The superposition becomes entangled with this vast environment, essentially instantaneously. Once this happens, the interference terms between dead cat and alive cat states become so diluted across the environment that they're impossible to observe. For all practical purposes, the cat is in a definite state, even though the full quantum description still includes superposition. Decoherence explains why we don't see quantum superpositions in everyday life. The environment acts like a continuous measurement, constantly pushing macroscopic objects into definite states. Decoherence also addresses the preferred basis problem. The interaction with the environment selects a pointer basis of states that are relatively stable under environmental interaction. For position measurements, this is typically the position basis itself. For energy measurements, it's the energy basis. The environment naturally picks out the basis in which classical behavior emerges. This is genuinely explanatory progress. Before decoherence theory, the emergence of classicality from quantum mechanics was mysterious. Now we understand the mechanism. And decoherence has been verified experimentally in beautiful experiments by Serge Haroche, David Wineland and others who won the Nobel Prize in 2012 partly for this work. But decoherence doesn't solve the measurement problem completely. It explains why we don't see superpositions, but it doesn't explain why measurements have definite outcomes. After decoherence, the full quantum state still includes all possibilities. The cat is still in a superposition from the perspective of the universal wave function. It's just that this superposition is now spread across the environment in a way that makes it unobservable. Decoherence explains the appearance of collapse without collapse actually happening. But then you still need an interpretation to explain what's really going on. Many world advocates claim decoherence vindicates their approach by showing how branches emerge naturally. De Broglie-Bohm advocates say decoherence explains why we can't see the effects of the quantum potential guiding particles in different ways. Copenhagen advocates say decoherence explains why classical measuring apparatuses yield definite results. Everyone claims victory, but the fundamental questions remain. Objective collapse theories. Making collapse. Real. Some physicists have taken a different approach. What if collapse is a real physical process, but one that's not described by standard quantum mechanics? What if we need to modify the Schrödinger equation itself to include spontaneous collapse as an actual dynamical process? The most developed versions of this are the GRW theory, named after Girardi, Rimini and Weber, and the continuous spontaneous localization (CSL) model. These theories add stochastic terms to the Schrödinger equation that cause wave functions to spontaneously collapse randomly, but very rarely. For individual particles, collapse happens so infrequently that you'd never notice. But the collapse rate is proportional to the number of particles. For macroscopic objects containing trillions of particles, collapse happens essentially continuously. This explains why microscopic systems show quantum behavior, while macroscopic systems appear classical. These theories make different predictions from standard quantum mechanics in certain extreme situations. They predict that quantum superpositions of sufficiently large objects simply can't exist, even if you isolate them perfectly from the environment. The wave function would spontaneously collapse. This makes objective collapse theories experimentally testable, at least in principle. Several experiments are underway trying to test these theories. They involve creating quantum superpositions of larger and larger objects, first molecules, then nanoparticles, potentially eventually microorganisms, and seeing if there's a size limit where superposition becomes impossible. So far, no evidence for spontaneous collapse has been found, but the experiments are difficult and haven't yet reached the scales where GRW and CSL predict deviations should appear. The main criticisms of objective collapse theories are that they're ADHOC modifications, introducing new unexplained parameters, like the collapse rate and collapse width, and that they struggle to be made compatible with relativity. Creating a relativistic version of GRW or CSL is an active area of research, but it's proven quite difficult. Quantum Bayesianism, cubism, making it about belief. A more radical recent approach is quantum Bayesianism, usually called cubism, developed by Carlton Caves, Christopher Fuchs, and Rudiger Schack. This interpretation takes seriously the idea that quantum mechanics is fundamentally about personal belief rather than objective reality. In cubism, the wave function represents an agent's subjective degrees of belief about what they'll experience in measurements. Collapse isn't a physical process happening in the world. It's an update of belief that happens in the agent's mind when they gain new information through measurement. Different agents can assign different wave functions to the same system. And that's perfectly fine, because the wave functions represent their different states of knowledge. This solves the measurement problem by denying that it's about physics at all. There's no mystery about why measurements yield definite outcomes. Outcomes are what agents experience, And of course, experiences are definite. There's no non-locality problem because the wave function isn't describing something physical that could act non-locally. Cubism is deeply influenced by Bayesian philosophy of probability, which treats probabilities as degrees of belief rather than objective features of reality. Just as two people can rationally assign different probabilities to the same event based on their different background information, two observers can assign different wave functions to the same quantum system. Critics argue that cubism goes too far towards subjectivism. If wave functions are just in observers' heads, what explains the remarkable fact that observers who follow the rules of quantum mechanics make successful predictions? Why does nature cooperate with our subjective beliefs? Cubists respond that there are objective facts about measurement outcomes, and quantum mechanics provides constraints on rational belief that ensure different agents' beliefs remain consistent with each other and with their experiences. Relational quantum mechanics, making it about relations. Carlo Rovelli proposed relational quantum mechanics, which shares some similarities with cubism but with important differences. The idea is that quantum properties don't belong to systems absolutely, but only relative to other systems. An electron doesn't have a definite spin in any absolute sense, but relative to one measuring device it has spin up, while relative to another measuring device oriented differently it might have spin down. Both descriptions are equally true because spin is a relational property, not an intrinsic one. This sounds bizarre, but Rovelli argues it's analogous to how velocity works in relativity. Velocity isn't absolute. It's always velocity relative to a reference frame. Different observers measure different velocities for the same object, and they're all correct. Relational quantum mechanics extends this idea to all quantum properties. When a measurement happens, the measuring device and the measured system enter a definite relation. That relation is real and objective. But it's not absolute. It's only definite relative to that particular pair of systems. From the perspective of an external observer who hasn't interacted with either system, they might still be in a superposition. This dissolves the measurement problem by rejecting the premise that there should be a single observer-independent account of what happened. Measurements have definite outcomes relative to the measuring device, and that's all we need to explain our experiences. Critics worry about whether this is truly coherent. If everything is relational, what grounds the relations? Don't we need some absolute facts to anchor the network of relations? And how do we ensure consistency between different observers' relational descriptions? Part 6. Why none of this works, yet the problem of consciousness. I've been dancing around this issue, but we need to confront it directly. Some physicists and philosophers think consciousness might be essential to solving the measurement problem. The idea goes back to von Neumann and, more explicitly, to Eugene Wigner. If you keep pushing the Heisenberg cut outward, trying to include more and more in your quantum description, you eventually reach human consciousness. And consciousness, Wigner argued, seems fundamentally different from physical systems. Conscious observation might be what actually causes collapse. This leads to a deeply weird picture where human minds play a special role in physics. Before conscious observers evolved, was the entire universe in a quantum superposition? Did consciousness cause the universe to have a definite classical history? Wigner actually believed something like this, though he recognized how strange it sounded. Most physicists are extremely uncomfortable with this direction. Bringing consciousness into fundamental physics seems like mixing categories that should be kept separate. And it has troubling implications. Do animals cause collapse? What about very simple organisms? Do you need human-level consciousness, or does any information processing count? Where exactly does consciousness come from if the brain is just particles following quantum mechanics? Some researchers, like Roger Penrose, have proposed that consciousness and quantum mechanics are deeply connected, perhaps with quantum coherence in microtubules playing a role in conscious experience. These ideas remain highly speculative and controversial, with most neuroscientists skeptical that quantum effects survive long enough in the warm, wet brain to be relevant. But the connection between consciousness and measurement refuses to completely go away. After all, it is true that we only know about measurement outcomes through conscious experience. And there is something puzzling about how subjective experience emerges from objective physical processes. Maybe these puzzles are related. The quantum to classical transition. A deep problem that cuts across interpretations is explaining exactly how and why classical physics emerges from quantum mechanics. We know it does. Our everyday experience is thoroughly classical, but the mechanism remains unclear. Decoherence helps, as I discussed, but it's not the complete story. Decoherence explains why quantum interference effects wash out for macroscopic systems, making them behave classically for most practical purposes. But the underlying quantum description still includes superpositions. We need to explain why the classical description isn't just convenient, but seems to be the right description for macroscopic objects. Think about it this way. When you throw a baseball, it follows a definite trajectory through space. We can describe this trajectory using classical mechanics with extraordinary precision. But the baseball is made of about 10 to 25 atoms, each of which is a quantum system. The quantum state of the baseball is a monumentally complex superposition of different configurations. Why does all that quantum complexity average out to produce a simple, definite classical trajectory? Why don't we ever see violations of classical mechanics for baseballs, even though the underlying description is quantum? Decoherence tells us why we can't observe the quantum interference terms, but it doesn't fully explain why the baseball acts as though it has a definite position and momentum at each instant. This connects to a broader issue called the problem of outcomes. Even if you accept that decoherence explains why different branches don't interfere, you still need to explain why, within any given branch, we see one particular outcome rather than a superposition. Many worlds addresses this by saying all outcomes occur in different branches, but then you need to explain the appearance of randomness. Copenhagen addresses it by postulating collapse, but without explaining what causes it. De Broglie-Bohm addresses it by adding hidden variables, but at the cost of non-locality. The incompatibility with relativity. Special and general relativity describe a universe where space and time form a unified four-dimensional structure called space-time. Events are only absolutely ordered as past or future if they're connected by time-like paths. Space-like separated events have no absolute time ordering. But quantum mechanics, at least as usually formulated, treats time very differently from space. Time is a parameter in the Schrödinger equation, not an observable like position. The measurement postulate describes an instantaneous collapse of the wave function, but instantaneous doesn't have an invariant meaning in relativity. Simultaneous in one reference frame isn't simultaneous in another. This tension becomes especially severe when you consider entangled particles at large spatial separations. When you measure one particle, the correlation with the distant particle's measurement appears to require faster-than-light influence. Einstein called this spooky action at a distance and considered it a serious problem, though he didn't live to see Bell's theorem prove that no local hidden variable theory can reproduce quantum predictions. Quantum field theory, which combines quantum mechanics with special relativity, handles this somewhat better. It describes particles as excitations of underlying fields, and the fields are local. But quantum field theory still doesn't solve the measurement problem. When you detect a particle, the field presumably collapses, and we're back to all the same issues. General relativity introduces additional complications. In curved space-time, defining a global quantum state becomes problematic. And if we ever develop a theory of quantum gravity, we'll need to somehow combine quantum superposition with the idea that space-time geometry itself is dynamical. This seems to require quantum superpositions of different space-time structures, which is extremely difficult to make sense of. Experimental inaccessibility. Perhaps the most frustrating aspect of the measurement problem is that different interpretations often make the same empirical predictions. Copenhagen, many worlds, de Broglie-Bohm, and others all reproduce the standard quantum mechanical predictions for all experiments we can currently perform. This isn't a coincidence. These interpretations were designed to agree with quantum mechanics predictions while trying to solve its conceptual problems in different ways. But it means we can't easily use experiments to decide between them. The measurement problem appears to be partly or entirely a philosophical question rather than a scientific one. There are some exceptions. Objective collapse theories make different predictions that could be tested with sufficiently sensitive experiments on large quantum systems. De Broglie-Bohm theory might show detectable deviations from standard quantum mechanics in certain situations. But these experiments are extremely difficult and haven't yet been performed at the necessary precision. The worry is that we might be stuck in a situation where we can't empirically decide between interpretations, leaving physics permanently dependent on philosophical prejudices. Different physicists choose interpretations based on what they find metaphysically palatable rather than on empirical evidence. And that's an uncomfortable position for a science to be in. Part 7. What's at stake? The nature of reality. The measurement problem isn't just a technical puzzle for physicists to solve. It forces us to confront fundamental questions about the nature of reality itself. Is reality fundamentally deterministic, with apparent randomness just reflecting our ignorance, as de Broglie-Bohm suggests? Or is randomness built into the fabric of nature, as Copenhagen and objective collapse theories claim? Do all possible outcomes of every quantum measurement actually occur in parallel universes, as many worlds insists? Or is reality somehow observer-dependent or relational, as cubism and relational quantum mechanics propose? These aren't idle questions. They affect how we understand what it means for something to be real. When we're not observing the moon, is it really there? Common sense says yes, and Einstein famously argued for this realism, asking whether we really believe the moon only exists when we look at it. But quantum mechanics challenges this intuition at the microscopic scale, and the moon is ultimately made of microscopic parts. The measurement problem also raises questions about the role of information in physics. Wheeler's it-from-bit hypothesis suggested that information might be more fundamental than matter or energy. If observers and measurements are essential to quantum mechanics, and measurements are ultimately about acquiring information, maybe information is the truly basic thing from which physical reality emerges. The arrow of time. The measurement problem connects deeply to one of physics' other great mysteries. Why does time have a direction? Why does entropy increase? Why can we remember the past but not the future? Most fundamental laws of physics are time-symmetric. The equations work the same forward and backward in time, but our experience of time is thoroughly asymmetric. Eggs break but don't unbreak. Mixtures don't unmix themselves. We age in one direction. Measurement collapse, if it's real, is one of the few processes in fundamental physics that's explicitly time asymmetric. Collapse goes from superposition to definite outcome, never the reverse. Could the arrow of time ultimately be grounded in the collapse of the quantum wave function? Or is the apparent collapse actually a consequence of the thermodynamic arrow of time through decoherence? This connects to the puzzle of the universe's initial conditions. To explain why entropy increases, we need to explain why it was low in the past. Why did the universe start in a special low entropy state? And what does that mean for quantum mechanics? Was the initial wave function of the universe in some particular state? And if so, why that state? Quantum computing and technology. The measurement problem isn't just academic, it has practical implications for quantum technology. Quantum computers rely on maintaining quantum superpositions in their qubits. But decoherence causes these superpositions to collapse into definite states, destroying the quantum information. The main challenge in building quantum computers is fighting decoherence long enough to perform useful calculations. Understanding the measurement process better could help us design more robust quantum technologies. If we understood exactly what causes collapse, or exactly how decoherence works in different materials and configurations, we could engineer better quantum systems. Moreover, quantum cryptography and quantum communication depend crucially on the properties of quantum measurements. The security of quantum key distribution comes from the fact that measuring a quantum system disturbs it. If we don't fully understand measurement, do we fully understand these security guarantees? There's also the question of quantum artificial intelligence. If consciousness is related to quantum measurement, and if quantum effects play a role in human cognition, then building truly intelligent AI might require solving the measurement problem first. Conversely, creating conscious artificial systems might give us new insights into the measurement problem by providing controllable test cases. The limits of science. Perhaps most troubling, the measurement problem might be telling us something about the limits of scientific explanation itself. Science progresses by observing nature, forming theories to explain observations, and testing those theories through more observations. But quantum mechanics seems to resist being fit into this framework. We can't observe quantum systems without disturbing them. We can't separate the observer from the observed. The theory seems to require something outside itself, either a classical realm or consciousness, or multiple worlds, or hidden variables, to be complete. This might indicate that a purely objective, observer-independent description of reality is impossible at the quantum level. Some physicists, like Bohr, were comfortable with this conclusion. They saw it as a sign of maturity in physics, an acceptance that nature has limits on what can be known. Others, like Einstein, found it deeply unsatisfying, a sign that quantum mechanics is incomplete and will eventually be replaced by a better theory. The question is whether the measurement problem represents a temporary gap in our understanding that will eventually be filled, or whether it reveals a permanent limitation on human knowledge. Can we ever have a complete, consistent, observer-independent description of quantum reality? Or must we accept that some aspects of nature will always require reference to observers, measurements, and experiences? Part 8. Recent experimental progress. Testing the limits of superposition. One way to shed light on the measurement problem is to push quantum superpositions to larger and larger scales, testing where, if anywhere, they break down. Over the past few decades, experiments have created superpositions of increasingly complex systems. In the early days, interference experiments with single particles, electrons, photons, neutrons confirmed quantum mechanics predictions. Then came molecules. In 1999, Anton Zeilinger's group in Vienna demonstrated interference with C60 molecules, buckyballs, each containing 60 carbon atoms and hundreds of electrons. These aren't elementary particles, they're complex composite objects showing wave-like behavior. Since then, interference has been demonstrated with even larger molecules, including complex organic molecules with hundreds of atoms. Teams are working toward creating superpositions of viruses and even bacteria. If successful, these would be genuine biological systems in quantum superposition, Schrödinger's cat getting closer to reality. These experiments test objective collapse theories directly. GRW and CSL predict that sufficiently large superpositions should spontaneously collapse on timescales that become shorter as the object gets bigger. So far, no such collapse has been observed. Superpositions persist exactly as long as standard quantum mechanics predicts, limited only by decoherence from environmental interactions. But there's still room for objective collapse theories to be true. The mass scales where they predict observable deviations haven't been reached yet. The real test will come if we can create superpositions of objects with billions or trillions of atoms, large enough that collapse theories predict significant effects. This requires extraordinary isolation from the environment and is at the cutting edge of current experimental capability. Quantum erasers and delayed choice. Another class of experiments explores the role of information in quantum mechanics. These quantum eraser and delayed choice experiments show something remarkable. Whether a quantum system behaves like a particle or a wave can depend on information that becomes available after the system has already been detected. The classic delayed choice experiment was proposed by Wheeler. You send photons through a double-slit apparatus, but you can choose whether to place detectors at the slits, revealing which slit the photon went through, destroying interference, or to let the photons pass unobserved, preserving interference, after the photon has already passed the slits. What happens? The interference pattern depends on your delayed choice. If you choose to measure which slit information, no interference appears, even though you made that choice after the photon passed the slits. If you choose not to measure, interference appears. It's as if the photon somehow knew what measurement you would make in the future. Quantum eraser experiments take this further. You can mark which slit a photon goes through, destroying interference, but then later erase that information, and interference reappears. The interference or non-interference depends not on the photon's physical path through the apparatus, but on whether which path information is available, even if nobody actually looks at it. These experiments don't violate causality. You can't use them to send information backward in time. But they dramatically illustrate how quantum mechanics seems to depend on information and knowledge in deep ways. They suggest that what matters isn't the physical disturbance of measurement, but the information gained or lost. This supports interpretations like Copenhagen and Cubism that emphasize the role of information and knowledge, but it's puzzling for interpretations that try to describe an observer-independent reality. How can whether a photon shows interference depend on information that exists elsewhere? Leggett-Garg inequalities and macroscopic realism. Another experimental approach tests whether macroscopic realism is compatible with quantum mechanics. Leggett-Garg inequalities, proposed by Anthony Leggett and Anupam Garg in 1985, are temporal analogues of Bell's inequalities. The idea is to test whether a system has definite properties at all times, independent of measurement, macro-realism, or whether measurement itself affects the system's state. You make measurements at different times and check correlations between them. If macroscopic realism is true, these correlations must satisfy certain inequalities. If quantum mechanics is correct, the inequalities can be violated. Experiments have tested Leggett-Garg inequalities on various systems: superconducting qubits, nuclear spins, photons, and even mechanical oscillators. The results consistently violate the inequalities supporting quantum mechanics over macro-realism. The systems demonstrably don't have definite properties between measurements. These experiments have been pushed to larger and larger scales. There are now Leggett-Garg violations demonstrated in systems with billions of atoms, operating at scales that would normally be considered thoroughly classical. Yet quantum mechanics continues to apply. There's no evidence of a scale where quantum behavior gives way to classical definiteness. This doesn't solve the measurement problem, but it constrains possible solutions. Any interpretation that tries to restore definite properties to quantum systems between measurements faces an uphill battle against this experimental evidence. Quantum entanglement over large distances. Bell's theorem and subsequent experiments have proven that nature is non-local, in the sense that measurement outcomes at one location can be correlated with outcomes at distant locations in ways no local theory can explain. But just how non-local is nature? Recent experiments have tested entanglement over increasingly large distances. Satellite-based experiments by the Chinese Misha satellite team have demonstrated entanglement between photons separated by over 1,200 kilometers. Ground-based experiments have shown entanglement between detectors separated by similar distances. These experiments confirm that quantum correlations persist over macroscopic distances with no observable degradation. The non-locality is real and robust. This is good news for quantum communication and quantum cryptography, but it deepens the mystery of how quantum mechanics can be compatible with relativity. Some experiments have also tested whether entanglement correlations could be explained by some kind of influence that propagates at a finite speed less than light. The answer is no. If there were such influences, they would need to travel at least 10,000 times the speed of light to explain the observed correlations. For all practical purposes, the correlations are instantaneous. This presents a challenge for any interpretation trying to avoid true non-locality. You can maintain locality within any given branch, as many worlds does, or you can accept non-locality explicitly, as de Broglie-Bohm does. But you can't have a single, local, definite outcome description that matches observations. Part 9. Philosophical implications. Scientific realism versus anti-realism. The measurement problem forces us to reconsider scientific realism. The view that our best scientific theories describe an observer-independent reality that exists whether or not anyone observes it. Scientific realism has been the default position of most scientists throughout history. When Newton described gravity or Maxwell described electromagnetism, they thought they were discovering true facts about a reality that exists independently of human minds. The success of science at making predictions seemed to confirm this view. But quantum mechanics challenges realism in multiple ways. In Copenhagen interpretation, quantum mechanics doesn't describe reality between measurements at all. It only describes measurement outcomes. In cubism, the theory describes subjective beliefs, not objective reality. In relational quantum mechanics, properties only exist relative to observers, not absolutely. Even many worlds, which might seem thoroughly realist with its infinite branching universes, challenges traditional realism. The reality it describes is radically different from anything in our experience. We never observe other branches, so what justifies believing they're real? Is it realism to postulate vast, unobservable structures, or is it just metaphysics disguised as physics? Anti-realist positions argue that science doesn't need to describe reality as it is in itself. Instead, science should be understood instrumentally as a tool for organizing our experiences and making predictions. From this view, the measurement problem isn't really a problem at all. Quantum mechanics is an extraordinarily successful predictive tool, and demanding more than that is asking science to do something it was never meant to do. But most physicists find pure instrumentalism unsatisfying. We want to understand how nature works, not just how to calculate answers. The success of physics at explaining phenomena, not just predicting them, suggests we are learning something true about reality. The challenge is figuring out what that something is in the quantum domain. Determinism and free will quantum mechanics is often invoked in discussions of free will. If the universe is fundamentally random, maybe that randomness provides room for free will to operate. But this connection is more problematic than it first appears. Classical physics, despite being deterministic, never really threatened free will in a clear way. Yes, if you knew all the initial conditions with perfect precision, you could predict the future. But nobody ever can know those conditions precisely. Practical predictability was always limited, leaving room for human agency. Quantum mechanics introduces genuine randomness, or at least unpredictability, at the fundamental level. But it's not clear how this helps with free will. Random events aren't freely chosen events. If your decisions are determined by quantum fluctuations in your brain, that's not freedom. It's just chance. You're not in control. Random quantum events are. Some interpretations restore determinism. De Broglie-Bohm theory is completely deterministic. Particle positions evolve according to fixed rules given the wave function. Many worlds is also deterministic at the level of the universal wave function. All outcomes occur with certainty, and apparent randomness is just ignorance about which branch you're in. But even in deterministic interpretations, our experience is of making choices in a genuinely open future. In many worlds, all choices are made. You'll experience only one outcome, but all versions of you make all possible choices across different branches. Does that constitute free will? The question becomes deeply puzzling. Perhaps the measurement problem and the free will problem are related. Both involve the relationship between physical laws and conscious experience. Both involve the appearance of definite outcomes emerging from physical descriptions that seem to allow multiple possibilities. If we solve one, we might make progress on the other. The problem of other minds. Here's a weird connection that isn't often discussed. The measurement problem has similarities to the problem of other minds in philosophy. You know that you are conscious, because you directly experience your own consciousness. But how do you know that other people are conscious? You can't directly experience their inner lives. You infer consciousness from their behavior, appearance, and reports, but you can't prove it. For all you can prove, you might be the only conscious being in a world of unconscious zombies that merely act conscious. Most people find solipsism, the view that only you are truly conscious, obviously false, even though it can't be strictly disproven. We solve the problem of other minds through inference to the best explanation. The hypothesis that others are conscious like you explains their behavior better than the zombie hypothesis. The measurement problem has a similar structure. In many worlds, you experience one outcome, but you can't directly observe the other branches where different outcomes occurred. How do you know those branches are real? In Copenhagen, you experience the system after measurement, but you can't observe it between measurements. How do you know it exists then? In both cases, we're trying to infer facts about unobservable aspects of reality from our limited observations. And in both cases, different philosophical positions, realism versus anti-realism, multiple worlds versus single outcome, make identical observable predictions but tell radically different stories about what's really there. Maybe this similarity isn't coincidental. Maybe both problems arise from the limitations of first-person experiential access to a reality that extends beyond immediate experience. And maybe both require accepting that some aspects of reality must be inferred rather than directly observed, even if we can't prove those inferences with certainty. Emergence and reduction. The measurement problem illuminates a deep tension in how we understand complex systems. We have two contradictory intuitions about how the world works. Reductionism says that complex things are ultimately just collections of simple parts following simple rules. To understand anything fully, you break it down into components and figure out how those components work. Chemistry reduces to physics, biology reduces to chemistry, psychology reduces to biology, and everything ultimately reduces to the fundamental laws of particle physics. Emergence says that complex systems have properties that their components don't have, and that can't be predicted from knowing about the components alone. Consciousness emerges from neurons. Life emerges from chemistry. Solidity emerges from atomic interactions. These higher-level properties are real and require their own explanations that can't be eliminated by talking only about lower levels. Quantum mechanics seems to support emergence. Classical behavior emerges from quantum behavior through decoherence. Definite measurement outcomes emerge from quantum superpositions. The macroscopic world emerges from microscopic quantum laws. But the emergence seems mysterious. We can't quite explain how or why it happens. If reductionism is true, classical physics should be derivable from quantum physics, and measurement should be explainable as a physical process describable by the Schrödinger equation. But we can't achieve this reduction completely. We need additional postulates like collapse or additional entities like hidden variables. If emergence is true, measurement might be a genuinely new phenomenon at macroscopic scales that doesn't reduce to microscopic quantum mechanics. But then we need to explain where emergence happens and what principles govern it. We'd be giving up on the reductionist ideal that has driven physics for centuries. The measurement problem might be telling us that neither pure reductionism nor pure emergence is correct. Maybe we need a more sophisticated framework that explains how macroscopic classical behavior emerges from quantum mechanics, while also explaining why that emergence is, in some sense, inevitable given the quantum rules, not just an accidental feature of our universe. Part 10. Future Directions and Open Questions. Quantum gravity and the measurement problem. Many physicists suspect that we won't fully solve the measurement problem until we have a theory of quantum gravity, a theory that combines quantum mechanics with general relativity. There are several reasons for this suspicion. First, general relativity tells us that space-time itself is dynamical. It curves in response to matter and energy. But if matter and energy are quantum mechanical, doesn't that mean space-time should be quantum mechanical too? What does it mean for space-time to be in a superposition of different geometries? This question becomes critical in cosmology. In the very early universe, quantum gravity effects were supposedly important. If we want to explain the universe's initial conditions, we need to describe the quantum state of the entire universe, including its space-time geometry. But describing the measurement of the universe's state is nonsensical. There's no external observer to measure it. Some approaches to quantum gravity might naturally solve the measurement problem. In some versions of string theory or loop quantum gravity, space-time might be fundamentally discrete rather than continuous, which could provide a natural cutoff where quantum behavior gives way to classical behavior. The holographic principle, which suggests that the information in a region of space is encoded on its boundary, might also shed light. If information is somehow more fundamental than space-time, maybe measurement is really about information transfer from systems to boundaries, not about physical collapse. But we're far from having a complete theory of quantum gravity, and even farther from understanding its implications for measurement. This remains one of the deepest open problems in theoretical physics: the role of time. Another avenue for progress might come from rethinking the role of time in quantum mechanics. The Schrödinger equation treats time as a parameter fundamentally different from space. But relativity tells us space and time should be on equal footing. This asymmetry might be related to the measurement problem. Some physicists, like Carlo Rovelli and Julian Barber, have explored timeless formulations of physics. In these approaches, time is emergent rather than fundamental. The universe doesn't evolve through time. Rather, correlations between different parts of the universe create the appearance of time flowing. If time is emergent, maybe measurement is too. Maybe the definite sequential nature of measurement outcomes is a feature of our emergent time experience, not a fundamental feature of reality. From a timeless perspective, all measurement outcomes might coexist in some sense, with time-ordered sequences emerging only for observers embedded within the universe. This is highly speculative, but it shows how rethinking our assumptions about time might open new approaches to the measurement problem. If we're wrong about what time is, we might also be wrong about what measurement is. Biological systems and quantum mechanics. An intriguing direction involves studying quantum effects in biological systems. For a long time, it was assumed that biological systems were far too warm and noisy for quantum effects to matter. Decoherence would destroy quantum coherence almost instantly. But recent research has found quantum effects in photosynthesis, bird navigation, and possibly enzyme catalysis. These systems somehow maintain quantum coherence long enough for it to be functionally relevant, even in warm, wet, noisy biological environments. If evolution has found ways to exploit and protect quantum coherence, maybe studying biological quantum systems will teach us something about the quantum to classical transition. Life exists right at the border between quantum and classical, and organisms have had billions of years to figure out how to navigate that border. Some researchers speculate that consciousness itself might depend on quantum effects in the brain, though this remains highly controversial. If true, understanding biological quantum mechanics might be essential to understanding measurement, since measurement and consciousness might be intimately connected. Quantum information theory. The information-theoretic perspective on quantum mechanics has been increasingly fruitful. Thinking about quantum systems in terms of information, what information they contain, how it's encoded, how it can be transferred, has led to insights and applications from quantum computing to quantum cryptography. Maybe the measurement problem should be approached primarily as a question about information. When measurement happens, information moves from a quantum system to a classical record. Maybe understanding the physical basis of information and how it flows between systems will illuminate why measurement seems special. Some researchers argue that information is not just a useful way of describing quantum mechanics, but might be ontologically fundamental. Maybe reality itself is ultimately made of information, and what we call physical systems are really information processing structures. From this view, measurement isn't special. It's just information transfer, which is happening all the time at all scales. This connects to ideas about the universe as computation, reality as simulation, and the digital physics program started by Edward Fredkin and pursued by Seth Lloyd and others. If the universe is fundamentally computational, maybe measurement is just a particular type of computational operation. Artificial intelligence and consciousness. As AI systems become more sophisticated, we face questions about machine consciousness that might intersect with the measurement problem. If we create artificial systems that genuinely have experiences, how does that relate to quantum measurement? If consciousness is necessary for measurement, do conscious AIs cause wave function collapse? Or would that show that consciousness isn't actually necessary, since we understand exactly how AIs work physically, and there's no special collapse-causing mechanism? Conversely, if we can't create conscious AIs, or if creating them requires something beyond classical computation, that might support views that consciousness and quantum mechanics are deeply linked. Maybe true consciousness requires quantum coherence, and purely classical computers can never be conscious. These are testable questions, at least in principle. As we develop more sophisticated AI and better understand the neural basis of consciousness, we'll gain insights that might bear on the measurement problem. The intersection of quantum mechanics, consciousness, and artificial intelligence could be one of the most profound areas of research in the coming decades. Part 11. Why this matters beyond physics. The nature of knowledge. The measurement problem challenges our understanding of what we can know. In classical physics, there's a clear distinction between our knowledge of a system and the system's actual state. We might not know a particle's position, but it has a definite position that we're ignorant of. Quantum mechanics blurs this distinction. The wave function seems to represent our knowledge, but it also seems to represent something real about the system. When we gain information through measurement, the system itself changes or appears to. Knowledge and reality become intertwined in ways that challenge traditional epistemology. This has implications far beyond physics. If even the most fundamental physical theory requires reference to knowledge and information, maybe knowledge is more basic than we thought. Maybe the subject-object distinction that philosophy has assumed for centuries needs to be rethought. Some philosophers argue that quantum mechanics supports various forms of idealism. The view that mind or ideas are more fundamental than matter. If reality depends on observation or measurement, maybe consciousness is primary and matter is derivative. Most physicists resist this conclusion, but the temptation is there. Certainty and doubt. The measurement problem also affects how we think about scientific certainty. We often hear that science proves things, that scientific facts are objective and certain. But quantum mechanics shows that even our most successful physical theory has foundational problems we can't resolve. This doesn't mean science is worthless or that all views are equally valid. Quantum mechanics makes extraordinarily precise predictions that are confirmed to incredible accuracy. The theory works beyond any reasonable doubt. But we don't fully understand what it means or why it works. This should instill intellectual humility. Even in physics, the most mathematical and precise of sciences, there are deep questions we can't yet answer. We should be cautious about claiming absolute certainty while still recognizing that some ideas are far better supported than others. The measurement problem shows that science is an ongoing process, not a finished product. We make progress, but new questions always arise. Each answer reveals deeper puzzles. This is how it should be. Science advances by questioning, not by accepting dogma. Technology and society. On a practical level, the measurement problem matters for quantum technology development. Quantum computers, quantum sensors, quantum communication networks. These technologies all depend on maintaining and manipulating quantum superpositions, which means fighting decoherence and controlling measurement. As these technologies advance, society will face new questions. Quantum computers might break current encryption methods, requiring new approaches to cybersecurity. Quantum sensors might enable surveillance capabilities that challenge privacy. Quantum networks might enable unhackable communication, with implications for national security and criminal investigations. Understanding the measurement problem better could accelerate these technologies or reveal fundamental limitations. If objective collapse theories are correct, there might be limits to how large quantum computers can scale. If many worlds is correct, quantum computation might be understood as parallel processing across multiple branches, suggesting new algorithmic approaches. Moreover, if measurement and consciousness are related, and if we develop artificial conscious systems, we might face ethical questions about quantum technologies that involve those systems. Do conscious AIs have rights? Can quantum experiments that involve conscious systems be ethical? These science fiction scenarios might become real questions sooner than we expect. Education and public understanding. Finally, the measurement problem has implications for how we teach and communicate science. Quantum mechanics is often presented in popular science as a collection of weird facts. Particles can be in two places at once. Observation affects reality. Nothing is certain until measured. These presentations capture something true, but they often leave people confused or skeptical. If we're honest about the measurement problem, we have to admit that physicists themselves don't agree on what's really happening. This honesty might undermine public confidence in science, or it might increase respect for science as a genuine inquiry rather than a collection of dogmas. Teaching quantum mechanics while acknowledging the measurement problem is challenging. How do you explain something you don't fully understand yourself? How do you convey both the theory's tremendous success and its conceptual difficulties? How do you avoid either oversimplification or overwhelming complexity? These educational challenges matter because quantum mechanics is increasingly important for technology, and because understanding science generally requires understanding how scientific knowledge is tentative and revisable, not absolute and final. The measurement problem is actually a great case study in how science works, not by providing final answers, but by refining questions and gradually approaching better understanding. Conclusion: living with mystery. So where does all this leave us? We've explored the measurement problem from multiple angles: mathematical, experimental, philosophical, practical. We've seen how different interpretations try to solve it, and why none of them fully succeed. We've examined the implications and the open questions. What can we conclude? The current state of affairs. First, let's be clear about what we do know. Quantum mechanics makes predictions that are confirmed to incredible precision. It correctly describes atomic spectra, chemical bonding, semiconductor behavior, superconductivity, superfluidity, quantum computing, and countless other phenomena. The theory works, and that's not in question. We also know that certain things are impossible. Bell's theorem proves that no local hidden variable theory can reproduce quantum predictions. Experiments confirm that nature really is non-local in the sense Bell meant. The Cauchy-Specker theorem shows that quantum observables can't generally be assigned definite values independent of measurement context. These are genuine insights about nature's structure. Decoherence theory has explained much about why we don't see quantum superpositions in everyday life, and how classical behavior emerges from quantum mechanics. This is real progress, even if it doesn't completely solve the measurement problem. What remains unclear? But crucial questions remain. We don't know whether wave function collapse is a real physical process or just an apparent one. We don't know whether the wave function describes objective reality or subjective knowledge. We don't know whether measurement is fundamentally different from other physical processes or just a special case of ordinary quantum evolution. We don't know if there are genuinely multiple worlds or just one. We don't know if there are hidden variables determining outcomes or if randomness is fundamental. We don't know where the quantum to classical boundary lies or if there even is such a boundary. And most fundamentally, we don't know what quantum mechanics is, telling us about the nature of reality. Is reality fundamentally indeterministic? Is it observer-dependent? Is it non-local, all of the above? Something entirely different that we haven't conceived yet? Why it's not solved? So why hasn't this been solved in a century of trying? Several factors contribute. First, different interpretations make the same empirical predictions for most experiments we can currently perform. Without experimental differentiation, progress is difficult. Philosophy and personal preference fill the gap where experiments can't decide. Second, the problem touches on deep issues that extend beyond physics. The nature of consciousness, the meaning of probability, the relationship between knowledge and reality, the status of mathematical descriptions. These aren't purely physics questions, and physicists aren't trained to handle them. Third, we might be missing key pieces of physics itself. The measurement problem might not be solvable within quantum mechanics alone. We might need quantum gravity, or a theory of consciousness, or some entirely new conceptual framework. Fourth, there might be sociological factors. Physicists are trained to calculate and predict, not to worry about interpretation. The practical success of quantum mechanics meant that foundational questions were often dismissed as philosophy rather than physics. Only recently has this attitude changed significantly. Reasons for optimism. Despite the difficulties, there are reasons to hope for progress. Experimental techniques keep improving, allowing us to test quantum mechanics in new regimes. Larger superpositions, longer timescales, more precise measurements. Objective collapse theories and some other interpretations make testable predictions that we're approaching the ability to check. Theoretical work continues on quantum gravity, quantum information theory, and quantum foundations. New mathematical tools and conceptual frameworks are being developed. Interdisciplinary work bringing together physics, philosophy, computer science, and neuroscience is yielding fresh perspectives. The rise of quantum technology has renewed interest in foundations. When you're building quantum computers, you can't ignore questions about decoherence, measurement, and the quantum to classical transition. Practical needs are driving foundational research. And simply having more people seriously working on these questions helps. For decades, thinking about quantum foundations was considered a career risk for physicists. That's changing. A new generation is tackling these problems with sophisticated tools and open minds. Living with uncertainty. In the meantime, we have to live with uncertainty. This is actually a valuable lesson. science isn't about achieving perfect final knowledge. It's about making progress, refining understanding, and honestly acknowledging what we don't yet know. The measurement problem has been unsolved for a century, and it might remain unsolved for another century, but that doesn't make quantum mechanics less valuable or less true in the ways that matter for practical purposes. We can use the theory effectively even without fully understanding its foundations. This parallels other situations in life. You don't need to understand neuroscience to successfully think and feel. You don't need to understand evolution to be alive. You don't need to understand economics to participate in markets. Systems can work without anyone fully grasping their foundations. But we want to understand. That's what drives science forward. And the measurement problem remains one of the most fascinating puzzles in all of human knowledge. A mystery at the heart of our most fundamental description of nature. A question that touches on reality, knowledge, consciousness, and existence itself. The path forward. Where should we go from here? Several things seem important. We should continue experimental work testing the boundaries of quantum mechanics. Every experiment that pushes superpositions to larger scales, that tests for spontaneous collapse, that probes the quantum to classical transition, potentially brings new insights. We should pursue theoretical work on quantum foundations from multiple angles. No single approach has solved the problem yet, so we should explore many. Modified quantum mechanics, new interpretations, quantum information theory, connections to quantum gravity. We should maintain intellectual humility. Strong opinions are fine, but dogmatism is dangerous. Different interpretations might each capture different aspects of truth. The answer might be something we haven't thought of yet. We should communicate honestly about uncertainty while also conveying what we do understand. Quantum mechanics is both amazingly successful and deeply puzzling. Both facts deserve emphasis, and we should remember what's at stake. The measurement problem isn't just an abstract puzzle for specialists. It's a question about the fundamental nature of reality, about what exists and how we can know it, about the relationship between mind and matter, about the limits of human knowledge. Final thoughts. I want to end with a sense of wonder rather than frustration. Yes, it's remarkable that we've been using quantum mechanics for a century without fully understanding it. But it's also remarkable that we've discovered a theory that works so incredibly well despite our incomplete understanding. The measurement problem shows us that reality is deeper and more strange than our intuitions suggest. The universe doesn't work the way common sense says it should. Particles really do exist in superpositions. Measurements really do affect systems in ways we can't eliminate. Reality really is weirder than we imagined. That's not a failure of physics, it's a triumph. We've probed nature deeply enough to encounter genuine mysteries, questions that challenge our most basic assumptions about existence. We've learned enough to know what we don't know. And the fact that the problem remains unsolved means there's still work to do, still discoveries to be made, still conceptual revolutions ahead. Somewhere, perhaps, is a young physicist or philosopher who will have the insight that cracks this problem open. Or perhaps it will take another century of gradual progress. Either way, the journey continues. The measurement problem reminds us that science is an adventure, an ongoing exploration of nature's depths. We may never reach final answers. Maybe there are no final answers to reach. But we can keep questioning, keep investigating, keep pushing the boundaries of understanding. And that's what makes this so exciting. After a century, the measurement problem is still not solved, which means the story isn't over. The deepest question in quantum mechanics remains open, waiting for new insights, new experiments, new ideas. Maybe you'll be the one to solve it. Or maybe your children will. Or maybe humans never will. But we'll make progress. We'll learn more. We'll get closer to understanding this fundamental mystery of existence. That uncertainty, that openness to discovery, that sense that nature still has secrets to reveal. That's not a bug in science. It's the whole point. The measurement problem isn't a failure. It's an invitation to think deeply, question boldly, and explore the most profound mystery at the heart of physical reality. Thank you.